I want Enrique to translate what I'm saying here.
Okay.
Yes, Enrique. Let's go through David Harris and Sarah Harris slides, but I want you to translate everything I'm saying. Okay, so now find Okay, so now let me. Okay, so let me. So right now. So right now I will show you slides which are based on this textbook by David Harris and Sarah Harris. So David Harris, he is working in a Harvard College. This is college in near Los Angeles. Yeah. So and this is his book, and I highly recommend this book because David Harris he is very practical engineer. So he was working in Intel doing Intel processor. And he together with Sarah Harris, who is not his relative, they just have the same last name, just like namesakes. They created a textbook which is mechanism extra. So this is like very plain, and this is up to date. So and it has like 5 books in one. So it has digital logic, verilog HDL, and it has how to build your microprocessor core. So can you just repeat to that?
Bien, muchachos, yo sé que la mayoría aquí habla inglés, pero ¿alguien entendió todo lo que dijo Yuri? ¿Sí? Sean sinceros. ¿Sí? Actually, they say they understand.
Okay, excellent.
Even the jokes.
Even the jokes.
Okay, now, yeah, so we just went through. Now let's go through his slides. So here is a chapter 4, and so this is the latest edition of this book. You may have some older editions. They have syntax of verilog 95,
Yeah.
but this is like more new.
Okay. But I think they have the same topics, right?
If you have first edition, yeah, topic is the same, but first edition has all the syntax, verilog 95.
Okay.
And second edition and third edition have a new syntax.
Okay, so this is the...
This is the newest. I can check what you have and I can tell. If you have edition 2, this is still fine, because they have also new syntax. but not at postage. So now let's go through this. So first hardware description languages, Verilog and VHDL. They appeared in the mid 1980s, and there was a Verilog and VHDL is another language, and this VHDL started as a part of military research in like 1981, and then it moved to civil area. So and now like all companies, including like Apple, Nvidia, Samsung, AMD, and so on, they do chips using system Verilog and VHDL, and now most of them do system Verilog. Yeah. So now. Yeah, and this allowed to do two things. One is synthesis, which we do today, and another is simulation. And yeah, so two types of modules. This is kind of not important now. Yeah, so you have a module which describes certain block, and module has inputs and outputs, and your code goes inside. Then you can make assignment operation with various operators like and or not. Here it shows how those values change in time in simulation, but we are not doing a simulation during this lecture. Yeah, this is synthesis. So I can just show you that if you write something like this, it becomes like electric circuit like this, with the AND and with OR and so on. So identifiers are case sensitive. So reset and recent are different words. Now, name should start with a letter, not with a digit. This is common, just like in C. Okay, so do you see that for some you need to translate?
I don't think so. Actually, they are familiar with those topics.
Okay.
¿Alguna pregunta?
It's just a review.
Ajá, the syntax.
Now, you also can put some modules inside other modules. So you can, this is called instantiation. But this is not like function call. When you do function call in C, you just stop executing one chain of instructions and go to a different one. But when you instantiate module in Verilog, you actually get piece of circuitry and put in another piece of circuitry. So on chip, it just becomes a block of transistors. So you can explain this. This is look like a call function called C, but this is not a function. It's putting a piece of hardware inside the so we have module here. Then we instantiate it inside another. This is not a function. This is just a block of hardware. We just put it inside another block of hardware. It can be multiple instances. So when you function call, you don't replicate the function multiple times. But here you actually replicate multiple times. So you put same piece several times.
Okay, so
yeah, so this is a vector which has some modules. Yeah, let me explain this point, because I'm not sure the slides explain it. No, the slides do not explain. So this module So basically what it's saying is that when you have module A and when you have like module B, and if you put multiple module A, A1, something then A, A2, something then A, A3, something then in Verilog, you are getting a piece of hardware which has 3 pieces of module A. So this module A is 3 times. This goes to hardware on a foundry. But if you write in C, if you write something like A function in C, and then when you write B and you call like A 3 times, then you don't create copies of this code. You simply create a flow where you call the functions and go back, then you call it again and go back and call it again.
That is in C.
Yeah, so this is in C. But in hardware, you actually put 3 pieces of hardware inside this module. This is an important distinction.
Okay, so it's not like you are calling the function.
Yeah, this is not a function call, this is just a physically putting several pieces of hardware.
Okay, so
This is just as if you get function and you just copy it code 3 times.
okay,
Yeah.
but here, for example, you have and 3 in B and 3.
Yeah, so if you, those are 2 different modules in this one. But if you instantiate this one here 3 times,
Okay,
this will be actually 3 pieces of hardware.
okay,
It's important point.
okay. So here, this is like my main module.
Yeah, this is a main
And
module, is also sub
I'm
modules.
calling the module and 3.
Yeah,
Yeah.
but you're not calling, you
Okay.
instantiate. So you physically get a piece of logic and you put it inside the module.
But when you say instantiate, I mean, it's not similar to call a function.
No, it's not. Because you see, when you call function in C function becomes bunch of instructions in assembly language.
Okay.
So if you have function A, and if you have function B, and if you call function B, then this goes to this code, and then it goes to beginning of function A and executes it, then it goes back here.
Okay.
And then if you call function A again, this goes to beginning here, executes it, and goes back here.
Okay.
So you have only one set of instructions for function A, but then you run it multiple times.
Okay.
But when you instantiate, you don't run a function, you simply copy blocks 3 times.
You replicate the models.
Okay.
Yeah, this is actually not absolutely necessary right now. It's just a side note.
Okay.
Yeah, so you don't need to make sure everybody knows
Lo que es importante es que cada uno de los módulos.
Let's go through.
Yuri, give Yuri.
Yuri, what you want to say?
Uh-huh. Yeah.
Just to clarify that in Spanish to them. Yeah. Cuando tienen ustedes una instancia aquí, esto se hace que es muy importante. Cuando están aprendiendo a programar y ustedes llevan una rutina, pues llevan la rutina y no ocupa más espacio en memoria. Pero cuando están hablando aquí de HDL en hardware, si ustedes quieren repetir que se hagan 2 veces las cosas, se copian. Y entonces implica más memoria, más espacio. Y por ejemplo, el chip que están usando ahorita es 9K, que dice que tiene 9000 celdas. Si ustedes agarran y tienen un módulo que tiene 100 celdas, y lo instancian 4 veces, ocupan 100 espacios por cada uno de ellos. Y entonces se reduce la capacidad que tiene su chip. Entonces aquí sí es importante que a nivel de hardware piensen que es pues, sacar y poner de nuevo hardware, o sea, una instancia, es copiar y van a usar más espacio y eso se va a correr en paralelo. Cosa que cuando nosotros hacemos una rutina 10 veces, pues todas las 10 veces es una después de otra. No sucede 10 veces simultáneamente. Entonces son dos cosas, espacio y paralelismo. ¿Sí les queda claro eso? Ok, sorry.
Okay, so here is an example of module which has input ports and output ports and many like assignments, just like what you saw. Got like AND, OR, XOR, then not AND, not OR. So next. Yeah, here is an operation called a unary AND. This is just a shortcut for a 8-bit vector, how to end all bit in one vector. This is not important right now. Yeah, this is a multiplexer. So this is sign of a multiplexer. This is we are choosing, putting to the output Y. We are putting either D0 or D1 based on selector. So next. Yeah, so this is what we discussed about adder. So if you want to add 2 bits, we can either use plus operation or we can use logic exclusive OR and the AND operation, and also find a carry, which is a carry to the next bit. So here I can actually show you one interesting thing. So so you see, so when you build like hardware, so suppose you want to like add multi-bit number. So
No, I did that. Do you need to
okay, yes, that's fine. So suppose we need to add like multi-bit number, like 1, 1, 0, 1. So this number 1, 0, 1, 0 is actually 10. So this is like decimal 10. This is actually 11. So like 10 plus 11 is equal to 21. So how we like add those numbers? You put 0 plus 1 is 1, and you carry 1 here, then 1 plus 1 is 3, and 3 is 1, 1, so you put 1 here, carry 1 here, and then 0 plus 0 is 0 plus 1 is 1, and then you put 1 plus 1 is 1, 0. So this is number 1, 0, 1, 1, 1, right? And the 1, 0, 1, 1, 1 is same as 16 plus, did I count this right? So, yeah, 10, 10 is decimal 10, and this is 11, so this is 21. So, 1, 0, 0, 0 is 16. Wait, I made a mistake. 0 plus 1, 1. Ah, yeah, there is no K here, so 1 plus 1 is 1, 0. So we have 1, 0, 1, 0, 1. So 1, 0, 1 is 5, and 1, 0, 0, 0 is 16. So 16 plus 5 is 21. Correct. So now if you want to add 2 binary numbers, you can build adder from several blocks doing full addition. So you just put like a form of a 2-bit adder. So you have like adder which adds a plus b 1 bit and make sum and make carry. And just like we add numbers in this way, we can put that we have like A0, B0, and put like A1, B1, and put like A2, B2, and put A3, B3. And then once we have like sum and once we have carry, we can propagate this carry here as like another input called carry or CI. So you can instantiate like 3 pieces of 1-bit addition and build multiple bit adder. So this is how it works. Yeah, I'm not going to do in details, but we will eventually explain
Yeah.
this.
Yeah. Well, actually, they are familiar with it.
Yeah, okay. Now, some of you had some issues with the precedence of operations, so which operation works first. So what it means is, so this is just like in C. So in C, if you write like A plus B multiply C, you need to put parentheses if you want to add first and multiply second. Okay, so just because one person made this mistake, I just want to make a note.
Yeah.
It's just a little bit.
Yeah, so what it means is that if you write A multiply B plus C multiply D, so this is treated as A multiply B plus C multiply D, but if you write A plus B multiply C plus D, this is treated as A plus B multiply C plus D. So multiplication operation always act before sum. Yeah, this is same as in C language, which you learn. And yeah, let's turn it go back.
Yep.
So this is what this like table is. At highest is mod, then you have multiplication, division, then you have plus and minus, then you have shift operations. So how many of you know shift operations from C or from other languages? So like half. So shift operation just means that you get a number as a binary number and shift to the left or to the right based on the direction of shift operation. Okay, so numbers. In verilog, so let's turn off. Okay. So in verilog, if you write some number, let's say if you write just 42, this number is usually assumed to be 32-bit wide. It's called like unsized, but most tools treat it as 32-bit. But if you want to put specifically 3-bit number, you write 3 apostrophe, and then if it's binary B 101, or if it's like decimal, you put G 6 decimal, or if it's hexadecimal, you put H. So how many of you know how to write and use hexadecimal numbers in C? Yeah, half. So yeah, so hexadecimal numbers are convenient for many operations, so you need to understand it. Yeah, so this shows that if you want to write binary, like number, like number 5 in binary is a 101, and you put 3-bit, which means it's 3-bit number, then you put apostrophe, then you put B, and then you put 101. So in our simple examples, we just put plain numbers like 42 or like 31, but in like professional code, we usually like always use precise number of bits to just reduce bugs that we have. Okay, now. Yeah, now this is important constraint. There is so as you already saw, these operations like 821 means bit slice. So we are getting number and get some part of this number. It's called the bit slice. So where is the link? Okay. So can we just explain just in case? So bit slice is that we are getting a piece of number by specifying left and right bit.
Yeah. Yes, aquí parte de lo que normalmente cuando hablamos en los lenguajes tradicionales, no segmentamos una palabra de 8 bits o de 16 bits, y aquí sí se vale hacer eso, en que ustedes están manejando, como son componentes, los pueden manejar uno a uno, cuántos bits quieren, qué es lo que está diciendo. La parte A es el bit, son 2 bits a partir del 1, la parte son 3 veces el B, que son 0 componentes, y cada uno de ellos se puede manejar de una forma diferente. Entonces, aquí sí es medio truculento. Normalmente es unos hace bolas, ahí les paso un tip, yo agarro el ChatGPT y le digo, explícame qué significa.
So yeah, so now you can also combine several bit pieces by using curly bracket number, comma, number, comma, number, comma, number. So plus there is a syntax how to repeat multiple bits. So three bits B2. So if you get this expression, you will get A2, A1. So you get A21, A2, A1. Then you repeat 3 times B0. So B0, 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 B0 3 times. Then you put A0, and then you put this constant 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0. Yeah, so this shows how to use such syntax, and you will use such syntax many times. Okay. So yeah, maybe you can reiterate this.
Yeah.
So concatenation operation and repetition. So you put several pieces in one.
Sí, o sea, aquí la verdad es que eso sirve para mapear en un momento dado todas las entradas y poderlas ver en un momento dado, en formas diferentes. Incluso pueden usar distintas variables para configurar diferente la interpretación en cada momento.
Yeah, so here is some like exercise on building multiplexer for building byte multiplexer for 8 bits using 2 multiplexers with 4 bits. I will not go in details. Once you learn this better, you can solve this exercise. This is good exercise. Yeah. Don't look at this slide. This is. This is about something which is not used now, in designs like what I'm doing. But this was which was used in like 90s, which is used now on the border of chip. Okay, delays you can skip, we are not going through delays today. Yeah, now sequential logic is something we are going to talk tomorrow. And yeah, but here talking about sensitivity is, yes, this is something we will talk tomorrow, or maybe like after lunch. So lunch combination. Yeah, so here is combinational logic using always board. Okay, so as we discussed, you can use construct called always comp, and always comp means that this block behaves similar to a program, which means that you can write a port with a logic, like output logic, and then you can put always comp and then put also like assignments here, right? So y1 is equal this, y2, y3, and so on. And so this is a way how to write instead of writing using assignment. So you see, if you go back to earlier slides, yeah, you see, so here you had several assigned statements, just multiple assigned statements. But you can also do it with you can also do it by writing always comp and then begin end and putting everything here. So this is just another way of doing it. Now here is a combinational logic using case. So we are doing a 7-segment display after lunch, and the seventh segment, here it shows that you can use a case operator. So case data 0, 1, 2, 3, 4, 5, 6, 7. It's the same as in C. You use switch operator. So switch conditions and case 0, case 1, case 2, case 3. So same thing as in C. Yeah, and you usually need to put default unless you specify all cases. Because if you forget, you will get a latch. I will not show what it is, but actually we saw. So this like screen moving with the noise. This was example of latch. So this happened when you forget to put default here. So this is like usually a bug. Okay, now there is such construct called case Z, and case Z means that you can put binary numbers with question marks, which means that you don't care about those bits. It's just a short way of putting cases. So instead of putting 4B 1000, 1001, 1010, you just put 1 and then question marks that you don't care about. Yeah, this is something not for now because it's more complicated. Assignment. Yeah, finite state machine. Okay, so how many of you know what is a finite state machine?
¿Han usado una máquina de estados finitos?
Okay. Yeah, we will talk about this tomorrow, yeah, because like Enrique wanted me to tell you, but I will explain this tomorrow. A finite state machine is some way of yeah, now like parameterized modules, we will not do it in this class because I intentionally decided to simplify it, but when you do like 1 year course, we usually put a parameterized modules, and it means that you can make widths of your inputs and outputs another signal to depend on some parameters. So right now like 7-0, like 8-0, but I put a parameter and put it width minus 1. Yeah. So, but you should learn this later on. Yeah, test benches, David Harris actually, test benches I don't like this. So this is fun. Okay, okay, so those are slides on basic syntax. Okay. So now, so what time is it now?
12:40. We have 20 minutes more.
You have